This video we'll be talking about vertical asymptotes, but it goes hand in hand with another video, probably your next video, about horizontal asymptotes. And we're going to take a look at these from the calculus perspective, because if you take a look at this, you'd say, well, I just made up a graph here, and you would say, well, yeah, that's a vertical asymptote. That's a horizontal asymptote right here. It is the line y equals 1, because this graph is getting closer and closer to it, but it never touches it. So you say, yeah, that's a horizontal asymptote. Same thing with the other part right here. This graph will just keep going up and getting closer to that vertical asymptote, but never touch it, so we have the vertical asymptote x equals 2. But by the time you're done with this video and the next video, you'll take a look at those and you'll say, aha, there's some calculus here. And just to give you a snippet of that, I would call this a horizontal asymptote because as I cruise out to positive infinity, my function's y values are getting closer and closer to 1. These y values are getting closer and closer to 1. We never actually get to 1, but remember, at a limit, we never care about getting to the spot. We just care about the trend as we get closer. Likewise, when I go on this vertical asymptote, as I'm getting closer and closer to an x value of 2, remember, as I go, I'm getting closer to an x value of 2, but I'm sneaking up from the positive side or the right side. So as my x values sneak up on 2 from the right, my function's y values are taking off to positive infinity. This calculus language describes the phenomenon of an asymptote that you learned about in your previous classes. So we're going to take a closer look. In this video, we're going to concentrate on the vertical asymptote, and on the next video, we'll concentrate on the horizontal asymptote. So here we have two very gangly looking functions, or graphs, or curves, and we're going to say, hey, is there a vertical asymptote there? And as we're doing that, I'm also going to point out this thing called a point discontinuity, which hopefully you're familiar with. Well, the first thing I would do in this case is I would say, you know what, this looks juicy for factoring, so I'm going to go factor. In fact, I'm going to do that to both of them, so I'll pause this. So you can see that I've factored both of these, and in this case it really makes quite a bit of a difference. If I look over here, those would reduce, and I'm left with this. And on the case over here, this, which would really be in parentheses if you want it to, those cancel. We get that. So let's take a look at the difference here. In this case, what I would say is I have a vertical asymptote at x equal at, let's see here. If it's a vertical asymptote, it is an x equals, yes, at x equals -5. But over in this problem over here, I would say I have a point discontinuity at x equals 2. So why the difference between those two? Here's why. When I first looked at the original functions, I couldn't really tell necessarily if there was trouble brewing, but when I got to the second line, now I knew for sure there was trouble brewing. Let me explain what I mean. Down here in the denominator, I have an x equals -5 and an x equals +2. That could cause problems in that graph. Over in this one, I have an x equals 2 that would cause problems in that graph. In fact, I could have spotted that right away. Well, normally when an x value causes your denominator to be 0, you know there's trouble. The two types of troubles you could have are vertical asymptote or point discontinuity. So in this case, here's how I kind of think of it in my mind. This x equals 2 is trouble. If the trouble spot cancels away, I'm going to end up with what's called a point discontinuity, which means this graph would look something like this. It would be going along la da 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 da. And then right at x equals 2, there's just a missing spot. That's a point discontinuity. And in this case, if I were to graph that, this would occur at x equals 2. Sorry. This would occur at point x equals 2. Whereas on this side, I see two trouble spots. I see an x equals 2 trouble spot and an x equals -5 trouble spot. If the trouble spot does not reduce away, like happens here and here, but the trouble spot remains, then that's going to be a vertical asymptote. So in this case, if I were to go over here to x equals -5, I know I'm going to have, I keep doing that to you, sorry. I know I'm going to have a vertical asymptote at x equals -5. I'm still going to have a point discontinuity at x equals 2, so I really don't know what this graph looks like, so I'm just going to make something up, know that this is not exactly true, but we'll say la da 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 da, x equals 2, point discontinuity, la da 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 da, vertical asymptote, and it would keep going. So what you need to know out of this section is if something was going to be trouble in the denominator, an x equals 2, an x equals 2, and x equals -5, then it's going to be classified as either a vertical asymptote or a point discontinuity, and you figure that out this way. If the trouble spot cancels away, point discontinuity. If the trouble spot remains, vertical asymptote. So now we have one final thing to do. All right, I have to confess, now there's trouble because someone came to the door and I had to pause this and my brain doesn't remember where I was. But what I think I want to do is start investigating this vertical asymptote. I know there's a vertical asymptote at x equals -5, but remember I just made that up. I don't know exactly what's happening at that vertical asymptote because when you have a vertical asymptote, I'm just going to draw a random one here. It could be that your function is going up that way, but it could also be that your function is going down that way. You don't know. And that's what the final part of this video is going to talk about. Here's a pretty simple function, and I know that it has a vertical asymptote at x equals 2. Here's why. X equals 2 is a trouble spot, but it doesn't cancel away. If it doesn't cancel away and it stays forever, then it's an asymptote. So to discover what this function looks like around this asymptote, I'm now going to do a limit. I'm going to sneak up on that trouble spot 2 from the right. And I'm going to sneak up on that trouble spot 2 from the left. In this case, it's a perfect time to use your intelligent t-chart or intuition. So I'm going to set that up. I'll pause while I'm setting it up. So here I've done the technique that I've called intelligent t-chart or intuitive limit. As I approach 2 from the positive side, it's like my x values are sneaking up on 2, but I'll never get there. As those x values get closer to 2, the 5 stays put, but this denominator gets tinier and tinier and tinier. I mean, imagine plugging a 2.0001 into there. It's just barely positive, close to 0. Well, this trend ends up going to positive infinity. Similar thinking, if you need to pause it to think about it, go ahead. But over here, I'm heading to a 5 divided by something that's negative but smaller and smaller and smaller. that would be a negative infinity. So these are two fairly straightforward limits, or at least they will be by the time that you're done with your limit chapter. And so now I'm going to put this into action up here. As I approach 2 from the right, my function is approaching positive infinity. As I approach 2 from the left, my function is approaching negative infinity. So, I don't know exactly what's happening over here, but I know eventually, as I get closer to 2, it's going to have to do that. We've covered a lot of territory on the vertical asymptotes here. This is going to pair up with the next video on horizontal asymptotes. See you later.